We all know how to define the term photoelectric effect at this point. So let's just go ahead and do 10.2. Let's take a look at the equation statement. Light of a wavelength 4.7 times 10 to the power 7 is shone onto the surface of a piece of metal. If the threshold of the metal is 4.37 times 10 to the power 14 Hz, calculate the maximum speed of an electron ejected from the surface of the metal. So let's take a look. We have the wavelength, right, of the light that is shown. And then we have the threshold frequency of the metal. And then we are looking for the maximum speed. We are looking for V max. This is what we are interested in. So how can we possibly combine all these formulas with all these variables, with one equation and solve for V max? Well, we know that E is equals to H plus constant multiplied by the frequency, right? But if you don't have the frequency and you have the wavelength, you can just use C divided by wavelength, right? C being the speed of light. So that is the energy, right? And then apart from that, we also have the energy being equals to the work function plus EK max. Well, the work function is just H multiplied by the threshold frequency plus EK max. EK max is a half mv squared. Well, not just any V, but V max, of which we are interested in. So the energy is equals to this equation, and the energy is also equals to this equation. So we can equate the two equations, as you can clearly see. We can say that Planck's constant, speed of light divided by wavelength, is equals to Planck's constant, threshold frequency, plus a half the mass V max squared. Right, we can do this because all these equations are equals to the energy. So now we can go ahead and calculate Planck's constant, that is 6.63 times 10 to the minus 34, multiplied by the speed of light, which is 3 times 10 to the power 8, divided by the wavelength. The wavelength is 4.7 times 10 to the minus 7 meters. This is equals to Planck's constant once more, 6.63 times 10 to the minus 34. Then the threshold frequency, we have 4.37 times 10 to the power 14 Hz, plus the maximum kinetic energy. So let's add it here, plus a half. The mass is the maximum speed of an electron that we're interested in. So the mass is going to be 9.1. Is it 9.1 or is it 9.11? Let's verify. 9.11 times 10 to the minus 31. Right. So 9.11 times 10 to the minus 31 multiplied by V max squared. So we are done with the physics. Essentially, we just need to solve for V max squared. So let's put these what is on the left hand side in the calculator first. So 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the power 8 divided by 4.7 times 10 to the minus 7. Okay, so on the left hand side I have 4.2511 times 10 to the minus 19. This is equals to, so now let's substitute these in the calculator. 6.63 times 10 to the minus 34 multiplied by 4.37 times 10 to the power 14. Yes, I'm just verifying to see if I'm substituting the right thing. So this is 2.8973 times 10 to the minus 19. And then we have a half multiplied by the mass of an electron. So it is just 9.11 divided by 2. So we get plus 4.555 V max squared. So let's take these to the left hand side. So 4.2511 minus 2.8973 is equals to 1.3538 times 10 to the minus 19. This is equals to 4.555 V max squared. So we can divide both sides by 4.555. Okay, I see the mistake I'm doing here. Right, I was surprised. This is 4.555 times 10 to the minus 31 V max squared. Right, so this is 4.555 times 10 to the minus 31 V max squared. So we are dividing both sides by 4.555 times 10 to the minus 31. So 1.3538 divided by, well, times 10 to the minus 19 divided by 4.555 times 10 to the minus 31. Let's see. 2.9721 times 10 to the power 11 is equals to V max squared. Let's take square roots on both sides. Let me convert it to scientific. I was getting a big number there. I'm getting 5.45 times 10 to the power 5 meters per second being equals to V max. So there we go. That is the maximum speed of an electron ejected from the surface. Okay, let's take a look at 10.3. 10.3. A simple electroscope consists of a zinc disc, a metal stem, and a thin length of gold foil. Right, a gold foil. When the electroscope is neutral, the foil hangs vertically as shown in diagram 1. Vertically, as we can clearly see here, it's hanging vertically, right, straight downwards. Okay, let's hear the stories. When the electroscope is negatively charged, the foil is repelled from the stem, as shown in diagram 2. So when it is negatively charged, it gets repelled a bit. Okay, let's hear the stories. When ultraviolet light is shown on the disc of the negatively charged zinc electroscope, the foil collapses towards the stem, hangs vertically. So when we have ultraviolet that is shown here, the foil starts to hang vertically. We're going to talk about why that is so in a few. First question, 10.3.1. How does the frequency of the ultraviolet light compare to the threshold frequency of zinc? Right, only higher than, lower than, or equal to? It is higher than. That is why the photoelectric effect is taking place. The question says, explain why the foil of the electroscope collapses. So, okay, let's take a look. When it is negatively charged, the foil, it gets repelled, right? And then we are told that when ultraviolet light is shown, the foil falls back. The foil is falling back because now it is neutral again. We know that when it is neutral, the foil hangs vertically. So why is it neutral from being negatively charged, right? It was negatively charged and now it is neutral. Why is that the case? It was negatively charged and now it is neutral. Why is it the case? That is because light of suitable frequency has been shown and then an electron has been ejected, right? So that is how we know that ultraviolet light has a frequency that is higher than the threshold, because an electron or electrons have been ejected. That is why it is no longer negatively charged and now it is neutral and the foil is falling back, right? And then 10.3.3, green light is now shown on another negatively charged zinc electroscope. The foil does not collapse. Will the foil collapse if the intensity of the green light is increased, right? Either yes or no. Give a reason for your answer. So the question is no. Oh, well, the answer is no, not the question. The answer is no. Why? If green light is not making the foil to collapse, it means that the green light is not of suitable frequency. The frequency is not high enough to eject the electrons. So if you increase the intensity, but the frequency is less than the threshold frequency, electrons are still not going to get emitted because there isn't enough energy to eject the electrons. So it doesn't matter what you do with the intensity. If the frequency is less than the threshold, no electrons are going to be emitted. So that is why the answer is no.